Good morning, good morning. Okay, so my name is Justine Bone. I'm a member of the review board of the Black Hat Briefings and the Black Hat CISO Summit. I'm also executive director of the Crypto ISAC. So I'm really excited to be introducing your presentation this morning called Hardening HSMs for Banking Grade Crypto Wallets. At the Crypto ISAC, we are endeavoring to facilitate information sharing as it relates to cybersecurity incidents impacting the crypto industry. So topics such as this are extremely important, and areas of research such as this are extremely important to us. So I hope that you're as excited as I am to hear this presentation. So it is my pleasure to welcome to the stage here JP Aumasson and Shervin Majuri. Enjoy the presentation. Thank you very much.
Thank you. Thank you, Justin. Hello, good morning. Mic check. Yeah, it's working. So we're going to talk today about how to leverage hardware security modules, HSMs, to protect money, to protect virtual money, what we call crypto assets. Crypto assets, it's cryptocurrency like Bitcoin. It's also tokenized securities like tokenized bonds. It's also stable coins. And it's not really for you as an individual managing like maybe a few thousands worth of Bitcoin. It's for banks and large financial institutions that manage maybe billions of dollars worth of assets, and which therefore need very high security assurance. So this is focused on this use case, but it's more broadly applicable, everything that we're going to say about HSMs. So I'm JP, I've been doing cryptography for 20 years. I've written a book. The new version is very good. You need to buy it. It's a fantastic book. I love it. It's not my first Black Hat talk, but I'm with Shervin, who is doing his first Black Hat talk today.
Yes, hello. Yes, I'm Shervin. I've been with the company for 5+ years, and hopefully our experience with HSMs will help you guys architecture your security needs. And now for GP.
Good. Okay, some small commercial break. Have you heard of the company Taurus? We're the best company doing hardware security for banks that manage crypto assets. And more seriously, so with everything we're going to present, almost everything we're going to present is being used in production, but also state. So it's not just us imagining stuff. It's really real technology. All right, so we'll start with what is an HSM, what is inside an HSM, then what is the attack surface, how can you attack an HSM, how can you talk to an HSM, and then how can you harden an HSM? How can you reduce the attack surface? How can you make it more secure for different definitions of secure? And finally, we have a small part about best practices that apply almost to anyone using an HSM, and we'll talk about cloud HSM or HSM as a service. So again, the disclaimer, we've been using 1 or 2 specific lines of HSMs. Not all HSMs are the same, obviously. They have some stuff in common, but you might have different experience with different HSMs. Okay, so how many of you have used an HSM before? Maybe raise your hand. Quite a few. Oh, okay, cool. So you roughly know what's an HSM. You know, it's a specific type of cryptographic security module. So a cryptographic security module, according to the NIST FIPS 140-2-3, it's something doing cryptography, which may be software or hardware. And a hardware security module, obviously, it has some hardware components, so stuff that you can touch, that you can see. It's not purely software, but it includes software. So one vendor is defining it as follows: as a dedicated crypto processor that is specifically designed for the protection of the crypto key lifecycle. So crypto processor, it means cryptography processor. Processing crypto, it means doing crypto, doing stuff like key generation, encryption, decryption, signature, MAC, and so on. The protection of the crypto key lifecycle. What is the lifecycle? The lifecycle, it starts with a key generation. You create a key out of the blue with a PRNG. Then maybe you provision this key into some HSM, you configure this key, you store this key, you use this key. Then you don't need the key anymore, so you delete the key, you generate a new key, you rotate the key. So key management is the hardest part of crypto. And if you've been doing crypto in practice, you know this very well. So how does an HSM look like? On the left hand, we have a photo of our test HSMs at the office. They're just 1 rack unique boxes. And on the right hand, you have a PCI Express card. So what's important to know is that we talk of these boxes as HSMs, but it's not really correct, strictly speaking, because the actual HSM is the module that is inside the box. It's not the whole appliance. So just to give her this small detail. Okay, so why do you use an HSM? Well, because you want more security, yeah, but concretely, the whole point of crypto using HSM, as I put it to our clients, is that even if all your workstations are compromised, even if all your virtual servers, your cloud VPS are compromised, all the software is compromised by the North Korean or whatnot, then they will not be able to extract the keys from the HSM. So you store secret keys, you store secret stuff in the HSM, and you ask the HSM, please sign this for me using the private key, or please decrypt that for me, or please encrypt that for me using AES. And you receive as a response the signature, the ciphertext, and whatnot. And the key stays in the HSM. And you have some security assurance that is supported by a number of security controls, specifically at the hardware level, some anti-tampering, so some tampering evidence, tampering detection, and to some extent tampering protection. So that's what FIPS 140-2-3 is about. So what do you use HSMs for? So I've mentioned the case of blockchain. You know blockchain, I guess, probably you heard about blockchain. It's been in the news for quite a while. In the blockchain world, you have a private key. It's your private key. If you lose a private key, you lose all your money. If someone steals your private key, they steal all your money. So you want to protect that key in terms of confidentiality and in terms of integrity. You also need to have backups. So you can use an HSM as a TEE, trusted execution environment. We'll get back to this later. But before blockchain, there was some cryptography before blockchain, and people use HSM for signing applications. For example, today, if you want to sign a Microsoft Windows application, you need an HSM, you need a FIPS certified module. For database encryption, you might have the key encryption key in the HSM. And maybe one of the main use cases is PKIs, whereby the root, the private key of the root of your PKI, like for certificate authorities, is in an HSM. Because if you were to steal this key, then you would obviously be in a very bad place and you want it to be protected. Okay, so how do you talk to an HSM? What are the interfaces, software or hardware? So I mentioned PCI Express. So you have your HSM card, you put it on a PCI Express slot, and boom, it works. There might be some USB connectivity on the HSM, but typically you will not use USB for using the HSM as a crypto processor. More commonly, there's TCP/IP stack, so you can talk TCP/IP to the HSM using the PKCS11 interface API we'll mention later. For admin operations, you also have different interfaces. You can SSH to the HSM. You can make HTTP requests depending on the model. With or without TLS, it depends. And you sometimes even have a graphical interface. Okay, so what's really inside in terms of security in crypto? Is the sound okay? I hear some small reverb. That's, okay, that sounds good. Okay, so what kind of security control do we have in an HSM to make it relatively secure? So you buy an HSM, you don't want to know the price. It's quite pricey sometimes. So maybe you want to use the same HSM appliance for different teams, for different applications, for different users. So you need kind of different accounts on your HSM. So these different accounts, they're called slots or partitions. So each of the slots or partitions has its own data space, its own users, its own security policies. And the idea is that if you're a user of slot number 2, then you're not going to see, read, or write the data of slot number 3 and 4 and 5 and so on. So this is an excerpt from one vendor's description of partitions, whereby it shows that you have different security policies and so on. There's some role-based access control are back, some kind of attribute-based access control as well. You buy an HSM, it's not like you have one root user and call it a day. So you have two kinds of admins. Typically, you have the administrator and you have the administration security officer. So the security officer, they could, for example, reset the initial PIN or password of the admin. They can set a public key as root of trust. They can do a few things, but not too much. The admin instead, they can do everything you can imagine an admin would do, like access the audit logs, reset the systems, and create users and that kind of stuff. And then for each slot, for each partition, you have one user token, one user account, and one security officer as well. So of course, in practice, you want to segregate these accounts. You don't want the same person or the same KMS to have all the credentials with the same permissions. You want different person, different account, different systems to have access to these different credentials. The PKCS 11 crypto key API. So it's the lingua franca of cryptographic modules. It just defines how your request should look like when you ask the HSM to encrypt or decrypt something, for example. So there's a specification which is quite boring to read, to be honest. It's a C-like specification with function prototype, with constants, with a bunch of signaling. And it tells you, for example, how to define that a key is only to be used for signature and not for decryption. It tells you how a request should look like, which bits you should set at which place, so that if you have, as a client software that talks to one HSM, and you want to use another HSM, then you can use the same stack, the same interface, and just use a different vendor's HSM because they speak the same language, PKCS 11. Okay. And last but not least, the infamous FIPS 140-2 and now -3 certification framework, which is split in 4 levels. The level 1 tells you that the cryptography is correct. And the level 2, level 3, level 4, it's about anti-tampering. So again, this is a certification. Sometimes people laugh, like, aha, you're FIPS certified, not completely secure. Yeah, that's the point. There's a scope, a set of controls, but it never means that it's absolutely secure. It just means that it fulfills the compliance criteria. Okay. And in an HSM, so many vendors have been around for quite a while, and they may not always implement the state-of-the-art exploit mitigation, so exploit in terms of software exploitation. You may not even have ASLR or data execution prevention. You typically don't have full-blown remote attestation, whereby you prove cryptographically that the output comes from a given program, but you can emulate it in different ways. And in terms of hardware, software, what you have inside, so you have silicon, you have a system on chip, you have a general purpose processor, that sometimes is a PowerPC core, so some big onion stuff, and some crypto accelerator. So what does it mean? Crypto accelerator is just some dedicated silicon that is doing the slow stuff of crypto, like arithmetic, like exponentiation, what elliptic curve and RSA will be using. In terms of software, you will typically find some basic minimal Linux distribution, some bootloader, some firmware update system, maybe some firmware anti-downgrade protection, and also some software. So when I was young and naive, with stars in my eyes, I saw that HSM were doing all the crypto in hardware with secure hardware, with advanced dynamic shielding and whatnot. But in fact, well, a significant part of the crypto is done purely in software using libraries like OpenSSL that everybody knows for better or worse. Okay. And yeah, it's doing cryptography, right? No surprise. What kind of cryptography? So all the standards, all the FIPS standards, well, most of them at least, so think AES, elliptic curve, NISP 256, ECDSA, SHA-2, SHA-3, and so on. And now also some non-FIPS algorithms, for example, ED2519, because it's used in many blockchains, that's one of the reasons. And now it's a FIPS standard, by the way, anyway. And what's the most important part in any cryptographic system? It's not encryption, it's randomness. Because if your randomness sucks, all your crypto is going to suck regardless of FIPS certification. So typically you have a true random number generator, something that samples entropy from the environment, and that generates random bits. And it's supported by some certifications. Okay, how to make this more secure? You can put some custom functionality sometimes. Not always, but in some models allow you to do that, which is pretty cool. And you have to develop it in C, in the C language. And of course, if you have bugs in your software, there will be bugs in the software when you're running in the HSM. So more power, responsibility, and so on. And it's quite limited in size. So you cannot put your whole AI LLM inside the HSM. Now, the elephant in the room where people talk about HSM and their security limitation is that, yeah, if you have the credentials to use the HSM, then you can use the HSM, obviously. So you want to protect the credentials that people use to access the HSM, the user credentials, the admin credentials, and so on. But you might add some security layers, as we explain later. And of course, if there are problems in PKCS 11 or its implementation, then there's little you can do about it as a user. Or maybe there is, as you will see. That's an example of a bug in YubiKey PKCS7 stack. And of course, today we all use open source for better or worse. But if you have bugs in open source software, then your HSM might end up being vulnerable. One small story, there was a regression SSH bug a couple of weeks ago. And we're like, oh, are our HSMs affected? Well, the good news was they were not. I mean, not so good news is that the OpenSSH was so old that they were not affected, but maybe now we have different problems. And something I want to mention is what I call the cross-slot attacks. You have these different slots, different partitions, but they use the same hardware. They share the same resources. So inevitably, you're going to have some security limitations in terms of information leakage. So all the Spectre meltdown stuff, you're going to have this kind of vulnerability to some extent. And all the supply chain issues that you can imagine if you run your own software in the HSM, and the randomness, again, maybe you remember the Roca bug in Infineon chips. I'll leave the stage to Shervin for the rest of the talk.
Yes. All right. So the rest of the talk is going to mostly focus on custom modules and what they bring to the table as far as security goes. But I thought we'd start by showing that, all right, they're not super tested within the HSM community. Since they run inside the HSM, they have wide-reaching access to the HSM's internals, but well, those accesses aren't necessarily always tested. So we've hit some very dubious bugs when developing for those. Probably the most egregious was the fact that logging too much, by the way, too much is like 10 lines a minute, would cause the HSM to completely freeze, and we would have to go to the data center physically and unplug it, replug it. Thank you very much. Not to say that there aren't bugs when you're not using custom modules, because we've had some very fun ones, but use at your own risk. All right, so custom modules can be used to very profoundly alter how an HSM is used, how it behaves. And one side note is that they will most often not work on cloud HSMs. And the reason is very simple. It's that since you're installing a custom module directly inside the HSM, it's running within the HSM, it has access to everything, it can override everything, it's very hard to decommission. I mean, to at least know that it's correctly decommissioned. So most cloud providers just prefer not to allow you to install them. That's not a big deal in our use case because, well, most banks aren't really interested in cloud HSMs either way. They want to run their own. So let's dive in. PKCS 11 is how you talk to HSMs, and it has a lot of functions. Just in the standard, there's tens, hundreds of functions. And it's even worse because vendors can add their own function to that. Now, your application will probably not need to use all those functions. It might need to use like, what, 5. You might want to encrypt, but not export keys, for instance. So using a custom module, you can reduce the attack surface down to the absolute minimum by just overriding all the unneeded PKCS 11 calls and disabling them altogether. That way, even if an implementation is super buggy, it's no big deal. You overrode it. It's disabled. Again, with the PKCS 11, one of the most important parts of configuration of an HSM is the labels and the attributes that you put on your objects, because that's going to define all the operations that you can do with those objects. Now, those are usually set once at creation time. There might be errors, especially if you create them often. I'm putting often in air quotes. But like even once a month, that's often enough that some errors might slip in. So Using custom modules, you can actually, every time you load one of those objects, check that it has the correct, at least the very minimum set of attributes that it needs. And that way, you can have some reporting, some alerting. You might want to error out altogether, and that way you can fix the broken configuration and limit the errors. One important aspect is that both the previous slide, this slide and the previous slide were about limiting PKCS11. Now, in most applications, you actually know ahead of time which keys you're going to need and what you're going to be using them for. And if you already know those, it might make sense to bypass PKCS11 altogether. Some HSMs offer you something that they call a file system, which is actually storage at the same layer as PKCS11 objects. So it's the same security guarantees, but it's not accessible from the outside. And that way, you can actually directly program all your access patterns inside the custom module, and no one can do anything to bypass that from outside the HSM. All right, so let's step back a tiny bit and come back to what an HSM actually does. An HSM, you put some keys inside it, you call it, you say, hey, sign this, hey, encrypt this. It's going to sign it, it's going to encrypt it. It's not going to check if you're encrypting sound data. It doesn't even know what sound data is. So really, it protects against keys theft rather than key misuse. For instance, if you're a new cryptocurrency startup and you implement your Ethereum wallet within an HSM, well, Ethereum and Bitcoin use the same signature scheme. So if you have your Ethereum wallet that uses an HSM, you can also use it to sign Bitcoin transactions. But maybe that's not what your business model calls for. Well, you can actually use a custom module to verify all the inputs that the HSM will sign. So the custom module can say, OK, so that looks like an Ethereum transaction. I'm going to sign it. Or that looks like not an Ethereum transaction. I'm not going to sign it. This comes at a small downside in that in preventing misuse of the keys, you make the theft slightly easier because your custom module can have bugs. So with those bugs come the risk of leaking secrets, of code execution, but those can be mitigated with like secure development practices. In the same theme, access control. The base access control of an HSM is extremely limited. You usually have a couple roles. So you have the crypto user, you have the limited user, one can create object, one can use created objects, but not really much more than that. So let's take an example of like a very basic access control that we actually had. So we want to cut our users into two distinct roles. One are administrators who are in charge of managing users, and the others are, well, regular users who are in charge of approving requests. What we're going to do is we're going to issue private keys to everyone, either in their phone, in YubiKeys, or purely in software. That doesn't really matter. Since there's only a few administrators for every hundreds of users, we can actually take only the administrator public keys, put them inside the HSM, and then a request simply consists of users approving the request, administrators approving the users, so binding the user with a specific public key. Then you send that to the HSM. The HSM verifies that the administrator have signed users with the public keys that the HSM knows, and that the user correctly approved the requests. And you're done. You can have very extensive access control with that. So you can have thresholds, you can have users belonging to different groups. You can do stuff like, OK, so if my transaction is above 1,000 francs, then, $1,000. You can actually say, well, OK, then we need 3 different users. If it's above 1 million, then maybe 10 different users, stuff like that. Now, I'm skipping over a very tricky point, is in that, well, admins sign users, but users leave companies. So you might want to be able to delete them. That's tricky, and we're going to come back to that later. But for now, one more benefit of a custom module is end-to-end encryption. So for many different reasons, you might not really want to have your application talk directly to the HSM. because maybe you have multiple different models of HSMs. And so you would need to have the application directly having multiple protocols, embedding multiple libraries. That's kind of messy. Maybe some of those libraries even have a tendency to crash every once in a while, which definitely did not happen to us. And well, this use case in engineering is super easy. Put a gateway in front of it. The gateway abstracts away the HSM, application talks to gateway talks to HSM, easy peasy. Except now you're in kind of the awkward situation where the HSM provides transport level encryption, but that's between the gateway and the HSM. So if an application talks through the gateway for the HSM, well, the provider of the gateway, who is not necessarily the same provider as the application, will be able to see all the data inside that. Well, again, custom module, and there's a lot of ways to do applicative level encryption, so end-to-end encryption with that. And last but not least, all crypto primitives are not created equally within an HSM. So HSMs are typically covered by FIPS, and FIPS covers a wide range of algorithms, but not all of them. And you can kind of trust that the FIPS audited algorithms are correctly implemented, that they're free of bugs. But for the not FIPS covered ones, you're kind of, maybe not. Who audited this? Do they really work? You can't really check. It's not open source. So what you can actually do with custom modules is pick and choose what you want. So maybe you want to use an open source library to do stuff like EDDSA. Maybe you want to use the HSM directly to do stuff like RSA, ECDSA over NIST curves, stuff like that. So again, custom module, you have the flexibility. You can pick and choose what you want. So at this point, we kind of looked at each other and were like, OK, so we're adding this, we're adding that, we're adding a bunch of things to these custom modules. So what's the end game? Where does it stop? What can't we add? Well, state management, that came to mind. If we think back a few slides before, I mentioned that stuff like invalidating a user given an admin approval was kind of tricky, because if an HSM doesn't have any state, well, anything that had been valid at any point in time will continue to be valid forever. You need state to prevent that. And that's tricky. Why is that tricky? Well, HSMs aren't really made to talk to stuff like databases, which is where traditional applications store their states. So you need to do that locally. Doing that locally has two major roadblocks. One is that even though I mentioned HSM's file systems, that is super secure, super nice, you can put whatever you want in there, well, it's very limited in size. It's still like 5 to 10 megabytes. So if you have millions of users, you're not going to fit millions of users inside that space. And the second point, which is even more important, is that you might not want to rely on a single HSM. You might want multiple. And as soon as you have multiple stateful applications that need to be replicated, especially if they are HSMs and cannot really talk to each other, you have an issue. Thinking back to our users, how can we encode like a whole set of millions of users down to a single tiny data point that we can then link back to say, OK, so this user is actually within that set of approved users? Some of you are probably thinking it, Merkle trees. Super simple. Very concisely, what you do is you take your users, you have millions of users, you encode them as leaves inside a massive tree. Each node in that tree encodes the hash of its children. And given the root of that tree, which is a single hash, so 64 bytes, you can then trace a path back down to your user that you want to verify, and you can actually verify that it's in there. So if you want to verify that one user belongs to an approved set of 1 million users, you can do that using maybe a couple of kilobytes by revealing like 20, 40 nodes inside your Merkle tree. Now, this is all well and good if the state is static. If your set of users is static, that's super easy. How do you deal with user changes, right? So Intuitively, it's kind of tricky. You have to take all the users, add the new user, recompute a whole tree, it has a new root, and you have to essentially, well, recompute a whole new tree every time you have a state change. Can we do a bit better than that? Yes, we can. And it's not even very hard. Actually, you can take, imagine here on the left, ooh, I see my mouse. Here on the left, we have a tree with 2 users. I want to add one. What I do is I just turn this user into a node, and I add my user next to it. Super simple. I now have a new state root, and I didn't ever have to reveal or to unpack the whole right subtree. So the right subtree might have hundreds of thousands of users, right? And I managed to add a user and recompute the new valid state root with just 3 users, 3 nodes, easy peasy. Now, I mentioned that the right tree might have hundreds of thousands of users, but the left subtree, so like this subtree here, that I see my mouse here, has only 3. And that's the problem of this approach. It's that, well, it leads to very skewed trees. And can we do better? Again, yes. Self-balancing trees have existed for a while now. They're documented, and they work really well. And we're going to talk a bit about red-black trees. And especially, we're going to try to combine Merkle trees and red-black trees to see if we can have the best of both worlds. So a Merkle tree on which you can do updates, and the updates can happen on like bits of the tree instead of having to do with the whole tree. So very simply put, a red-black tree is a type of binary search tree. The binary part means that every node has 2 children, and the search part means that given a node, every node in the left subtree will have labels that are smaller. Every node in the right subtree will have labels that are higher. And on top of that, according to their name, every node is colored one of 2 colors, red or black. And then the tree itself follows 2 very simple rules. So given a node, any path down to any leaf has the same number of black nodes alongside it. This is called the black height of a node. And the other rule is that there cannot be an edge between 2 red nodes. Now, the red-black trees are interesting because all their rebalancing operations, so when you do an insert and you need to fix back the red-black properties, happen with rotations. And rotations, if you see here in diagrams, we have 2 nodes, 2 full nodes, and 3 subtrees. So we don't really need to unpack those subtrees, right? We can perform rotations without knowing what's inside those. And crucially, if those nodes, if those subtrees are actually Merkle trees, they stay Merkle trees. They don't change. So if we can do rotations, and rebalancing a red-black tree happens through rotations, and rotations keep Merkle structures, then you can kind of see where we're going with that. Now, let's test that intuition by looking at a few examples of insertion. So insertion happens by taking a node, inserting it at the leaf as a red node. Since it's a red node, the first red-black property, so the black height one, is not impacted at all. One that can be impacted is RB2, so the edge between 2 red nodes. So essentially, we're going to go recursively alongside the tree, fixing up this red-black 2 property. A simple case is this one. We're handling node X. We're fixing the RB2 property, so we have an edge between P and X. We're not too happy about that edge. We want to fix that up. How do we do that? Super easy. You recolor both the parent P and the uncle U to black. You recolor GP to red, and you're done. You now jump up the tree to GP, and you fix up the RB2 property from GP. Another case to see that, well, again, easy. This time, the uncle U is black. So you can't really just recolor P and U and GP and be done, because the black height of the node will be kind of violated. So we start off like before by recoloring P, recoloring GP, but we need to fix up that black height somehow. And that happens through a rotation. So we rotate GP one right, and as you can see, again, subtrees A, B, C, U, those don't need to be revealed. We don't need to have access to the data that's inside that. And if they're Merkle trees, they are still Merkle trees. And nothing is really impacted. So you can, again, we were able to add a value inside that tree and fix up the red-black property without really altering the Merkle property, which is kind of magical. One last case is the same as before, except X is the right subchild, is the right child of P. You rotate P to the left, you go back to exactly the same case as before, and you fix it exactly the same as before, and you're happy. So essentially what we're able to do is combine the red, black, and Merkle properties within a single tree. What that allows us to do is, imagine you want to insert one user within a set of 1 million users, and you have that set of 1 million user encoded as a tree. You can actually add that user by processing a subtree of maybe 20 to 40 users. You don't have to have the whole 1 million set. And that's pretty magical, and it lets us handle basically any state changes from inside an HSM without using any memory. And that's what we do.
Cool. Thanks, Sharon. That's really powerful stuff and more simple than it looks. It may sound a bit hairy with all the trees and stuff, but putting it in practice is not that hard. It doesn't make things more complex in terms of key management, and it really makes your life easier. And also in terms of security, this verifiable transition is really great to have. So to conclude, with 3 minutes left, the best practices, the boring, simple stuff that looks easy on the face of it, but which is very hard to do all the time, every day, for many years. Of course, you need to update the firmware. Duh. Who would not do that? But do it all the time for all your HSMs. It's harder. Have very tight PKCS11 attributes. You have a key that's used for signing only. So don't authorize the key to be used for decryption. That kind of stuff. Again, it's harder than it sounds in practice. Enable security features, see what the HSM offers, and see what that actually means, because it's not always very clear. And of course, good SDLC hygiene, good CI/CD, good software integrity. For example, one thing that we do when we do the build of our custom module, we don't do it automatically on Jenkins or whatnot. We sit in a room, a special computer, a special Docker container, and there's me, and there's Shervin, and maybe another guy, and there's one external auditor who verifies that the container is the right one that we build on it for this purpose with a specific software version. Everything is auditable, transparent, so you got to do the things right. Against access control, we mentioned it before, don't share the credentials with all your company. Manage the keys and do backups. Don't trust an HSM. No. You might have 2 or 3 redundant HSMs, but you might run out of luck one day, and boom, all your HSMs are dead. Oops. You need to have backups. You need to test backups. You need to verify backups integrity. You need to do backup recovery testing. If you manage billions of dollars worth of money, you want to do this right all the time, audited, documented, and so on. And that's very hard to do all the time. And you might have to worry about HSM cloning. There might be some cloning features. You may or may not want to use it depending on your risk model. And to conclude, a note on HSM as a service, so HSMs that are somewhere in the cloud. It's very convenient because you can say, oh, I use an HSM without having to buy and configure and touch an HSM yourself. It's really cool. And you access it via the middleware of your favorite cloud provider, all the famous ones. It might be multi-tenant if you go the cheaper option. You might just have a slot, a partition, on a physical appliance shared with other people that you don't know, which may or may not be a problem depending on what you're up to. And you have very little freedom in configuring the HSM, and of course you cannot put a custom software module, you cannot extend the firmware, because it's not your HSM. So most of the stuff that we presented is not applicable to cloud HSMs. And last but not least, how are you sure that it's a real HSM and not an emulator? You know, good question to ask. So to conclude, HSMs are very powerful. In HSM logic is very powerful, but you got to know what you're doing. You got to do it right all the time. You have to have a high maturity in your organization to do a good SDLC and understand very well what your HSM vendor, what your HSM model is doing. What's inside, what's the code inside, what's security limitations. So no bulletproof technology. So thank you for listening to our HSM talk. Thank you to the people who helped us. Thank you to the people at Taurus. And we'll be around for questions. Thank you.